Hi, today we will continue with the physics of torques. But in addition... Hello, today we are going to continue with the physics of torques. However, in addition to torques, in today's video we will also carry out a simple measurement of the depth of the snow and the mass of the snow. These measurements will help us to determine the weight of the snow on my balcony outside, and we will also use it to estimate the torque that the snow exerts on a pivot point where the balcony is attached to the building. So it should be a lot of fun. Let's get started. Here is snow accumulation on my balcony. This is a lot of snow and I should probably clean it. But it is very useful for the calculation that we will carry on. Firstly, notice that there is balcony above my balcony, which means that this snow over here had to be advected by the wind and not falling vertically. We will assume that the layer of the snow is uniform along the balcony's depth or width, whatever you want to call it, despite the fact it's not. As you can see, there is a difference in height because this metal rod over here and the underlying snow. And this is logical. The closer we are to the building, the less snow. But this difference is actually very, very small, so we will assume it doesn't exist. So what I have to do right now is I have to go into the snow and measure the depth. Unfortunately, I only have this small ruler, so this will be very, very difficult process for me and very cold. So let's do it. Again, I don't have gloves. Oof, very, very cold. Here is a ruler, 15 centimeters. So this is 15 and another 15, 30 centimeters. So two lengths of this ruler, 30 centimeters of the snow on my balcony. I made a mess, but what can you do? Anything for science. So the bad news is that I forgot to carry out measurements of the mass of the snow when I did these measurements of the depth of the snow. So I waited until the day after and I carried out the measurements of the mass that you will see right now. That was the bad news. The good news is that there are no more bad news. Now we also need to measure density of this snow, and my cat agrees. Right? Yes. So I'll take 1 cup and I need to measure first the mass of the snow. Mass 58 grams. Now we can go ahead and calculate the density of this parcel of snow. Here is a sketch of my balcony. Balcony is sticking out from the building. The attachment between the balcony and the building I will call P, pivot point, around which I will calculate torques. Positive torques are counterclockwise by convention, and the positive Z direction is up. Here we have weight of the balcony as the force, weight of the snow as the force, and this line, black line at the end, is the fence on the far side of the balcony, and I decided to account for that too. length of the balcony is 1.5 meters, I measured it, and the width of the balcony that goes into the page is 3 meters, I also measured it. Together we measured that the depth of the snow is 30 centimeters. Moreover, I estimated that the mass of the balcony is around 2,300 kilograms, accounting for the dimensions and the type of the material that was used in the construction. Mass of the fence, similarly, I estimated to be around 150 kilograms, and these numbers agree quite well with the online resources. We just measured that the mass of the snow in the cup was 58 grams. We know that one cup is 0.24 liters, and the liter is 1,000 times smaller than a cubic meter, so we get that this is the volume of one cup. Now let's calculate the volume of the snow on top of the balcony. Well, volume of the snow on top of the balcony needs to be the length of the balcony times the width of the balcony times the height of the snow. So here it should be subscript S. Height of the snow above the balcony. And we have all these numbers right here. So if we plug this in, we get 1.35 cubic meters. Now we can go ahead and calculate the mass of the snow on the balcony to be density of the snow times the volume of the snow. But I do not know density of the snow yet. However, I have these measurements that we just carried out, and they say that density of the snow is mass of the snow in the cup divided by the volume of the cup, and we have these numbers, so if we plug in, we will get that the density is 242 kilograms per cubic meter. This is a very important number because it allows us to compare these results with the literature. Here I printed from Patterson's book, The Physics of Glaciers, typical snow densities, the left column, and on the right column you see characteristics of types of the snow. We see that the fresh snow has typical density between 50 and 70 kilograms per cubic meter, and then as the snow gets older, the density increases. This snow is around half a day, more than half a day old, which is settled snow, and indeed we see that our value of 242 kilograms per cubic meter fits quite well between 200 and 300, which is settled snow on the ground that is characterized by some temperature variations. Now, when we have this density, we can go ahead and calculate that the mass of the snow on the balcony is this times volume that we calculated, and that is 327 kilograms. With these two numbers in mind, we can proceed and calculate the force here at the attachment between the balcony and the building that needs to exist to balance these three forces that are acting down. And I will calculate that, I will call that force Fp. We know that sum of all forces needs to be zero because nothing is moving, statics. Well, the only force that is acting in the positive z direction is Fp. So we have Fp, and the other three forces are negative, minus Fb, minus Ff, and minus Fs. And that needs to be equal to zero in order for this structure to be static. Well, all these forces, Fb, Fs, and Ff, are weights, which means from here that Fp is simply equal mass of the balcony times G plus mass of the fence times G plus mass of the snow times G. And now we can just plug in these numbers because we have them here and see that force that is necessary here at the attachment to counterbalance all these three forces is 27,215 newtons. That is a lot of force that needs to counterbalance these three. In a similar fashion, we can calculate torques, namely using the principle of static that the sum of all torques needs to be zero. Well, you will observe here that snow, balcony and fence are creating negative torque. Namely, they want to twist the balcony in this way, which is clockwise direction, which is negative torque. So there has to be positive torque around the pivot point P to balance these three negative torques, which means we can say that torque around pivot point P in the positive direction minus torques due to balcony itself minus torque due to fence and minus torque due to snow need to be zero. Very well, that means that torque at the pivot point P is equal these three. Well, torque due to balcony is the half length of the balcony times force of the balcony minus torque of the fence is the length of the balcony times weight of the fence and plus, and torque due to snow load is the half the width of the balcony times weight of the snow. Let's just remind ourselves why is here half of the length, because these two forces are acting from the center of the mass of the balcony and snow, and center of the mass is in the middle of the balcony, whereas the fence is positioned at the end of the balcony, so the arm of the force is the whole length of the balcony. We have all these numbers above, so if we plug in, we get that the torque is 21,513 Newton meters. I hope these calculations helped you to better understand torques, weight, and some simple measurements of snow, density of snow, and so on. I would also like to emphasize that here we implemented various assumptions in real structural analysis. These calculations are carried out using numerical approach, namely numerical models. I would also like to emphasize that in order to get precise values of the loads and bending moments and so on, you need elasticity of the material, way better estimates of the mass, stiffness, and so on. And also the balcony is not attached to the building as we described here. Balcony is rather extension of the ceiling, and the distribution of forces is not exactly like this. But the goal of this video was not to help you to construct your balcony, but rather to help you to understand the physics of torques and weight. I also checked the regulation for the balcony requirements, and it says that the new balconies need to be able to withstand around 450 kilograms of mass per square meter. The snow on my balcony is around 70 something kilograms per square meter, which means I can let snow fall, and I am way below the threshold when the balcony will collapse, at least under this snow load, accounting for this density of the snow that we calculated. At the very end, in order to make sure that I carried out all measurements correctly and I didn't mess up some of the depth and mass measurements, I sent inspection.